Good afternoon, everyone. So I once again thank you, Dr. Joshi, for your kind words in the introduction. Firstly, I would like to express my gratitude to Triple IT Sri City and the organizing committee for this workshop. Professor Arun and Professor Sanodia, who have been interacting with me for organizing this session. So thank you for this opportunity to present my research on this platform. Great. So yeah, let's get started. So I welcome you all to the session on knowledge graphs driven remote sensing scene understanding. So the intent behind this session is to share with you all the research advances that I have been working on throughout my doctoral research and some of the work that we as a collective unit in our lab at IIT Bombay have worked on. So the session has been titled as knowledge graphs driven remote sensing scene understanding. So before we move on to the aspect of knowledge graphs, let's talk a bit about scene understanding. So what essentially is scene understanding? So I invite all of you to pay your attention to the image on the left-hand side. So what I'm trying to get here is that I would like you and me as humans to look at this image and try to form a story in our minds by looking at this image. So like let's take a look and try to form a line of thought on what we interpret when we look at this image. So you can see that the then US President Obama, who is pulling a prank on one of his subordinates, who is in turn weighing himself on the weighing scale, right? So the one leg that the President Obama has put on the weighing scale is meant to increase the weight that the subordinate is weighing himself, and the other people in the room have realized this prank, and they are, they are laughing at this, right? And we as humans also have no difficulty in interpreting the fact that there are two sets of mirrors in this room, and the mirrors are essentially reflecting the people in this room who are in black and blue suits, right? But the same cannot be the case for a machine, right? So complete understanding of an image has always been the ultimate goal of computer vision since its inception. So on moving this image to the left, we humans are easily able to deduce this entire story of the then President Obama trying to pull a prank on one of his subordinates, right? But the machines in the current research progress, right, have yet to form their understanding of context from this image. So more on this as we proceed ahead, but the idea of computer vision throughout these years has always been to make a machine understand the context behind an image and try to form a story from the image itself, right? So with that objective, we slowly transition to the domain of remote sensing. Archives of remote sensing imagery have been captured throughout the years, and they have been known to have great potential in understanding numerous natural as well as man-made phenomena. The rate of data exploration, however, is far behind the rate at which this data is being generated. So the data captured by numerous remote sensing platforms, right, like satellites, there are airborne platforms which have high resolution cameras over them, and there are of course these the popular drones that are very popular nowadays. So these remote sensing platforms have the ability to capture data in very high resolution, but have we developed efficient algorithms that are enough to actually leverage the data that is being captured and explore the data so that some actionable insights can be transformed from it? So with that understanding, I would want you to pay attention to the satellite image to the left-hand side. So we as humans, if we look at the satellite image, we can easily interpret that this satellite image is actually or is captured during a flood event. To be precise, it is an urban flood event. So looking at the building structures that you see in the satellite, right? So we can say that with some surety that this could be an urban setup. And then there is an unaffected road towards the left-hand side of the image that we can see here. There are some vehicles too on this road. So there are many of these, insights that we as humans were very easily able to understand and deduce simply by looking at this image. But can the same be achieved by a machine? So this particular automatic understanding of context has always been the goal that has been, largely overlooked in the domain of computer vision. An enhanced understanding of remote sensing imagery and the machine level is desirable and could prove to be of great significance across a variety of domains. Coming back to the very topic of scene understanding, so let's formalize the objectives that we wish to achieve by automating this process of scene understanding. So to put it in a formal manner, one of the primary objectives would be to represent the scene in a machine readable form. So the machine readable form should be amenable for integration with other sources, and most importantly, it should be queryable by machines. It should be represented in a manner that is understandable by humans too. And natural language is the most easily understood form of data that a human can comprehend. So we would like the image or the scene to be translated in natural language to depict the scene descriptions. And the third objective being querying over the scene in a human readable form. So we would like the image, or rather the machine, to parse the image and be able to answer natural language questions when asked over it. So with these three objectives of scene understanding being formalized, we would like to discuss and elaborate more on the research advances that have been done so far. So with this, I'm sure, since this entire workshop is like on the topic of deep learning, this begs the question, and a very natural one, right? Can deep learning help to translate the images in a form that are machine readable, that are amenable for integration, that can answer questions in natural language? So that is why let's elaborate on this question. Can deep learning help? So I would like to run you through some of the recent advances in the domain of deep learning, where they have leveraged deep learning to translate a 2D image into an English language sentence. So this is a popular work that was published in an IEEE journal. So back in 2015, in the yeah, correct. So the title of this work is Show and Tell. So I believe this was Google's work that they had published in this particular journal. So the idea was to translate a 2D image using a combination of convolution neural networks and a recurrent neural network to generate an English language sentence. So as you can see from the figure here, the CNN, the Vision Deep CNN, essentially translates the features from the image and then uses those features as an input to the recurrent neural network that eventually generates the English language sentence. So to give you an example, this image that you see on the left is probably of a vegetable market, right? So the English language sentence that the neural network generated was a group of people shopping at an outdoor market. There are many vegetables and the fruit stand. So these were, simple sentences that the neural network, or rather the system that was proposed in this research paper, was able to generate looking at this image. So one important point to note here is that although the system was effective to that extent to generate a single sentence from a 2D image, the important point here is this: such a system would require a lot of data to be fed in, so that the neural network is able to understand the image as well as the type of sentences that it needs to generate, right? So this was one of the milestone works in the domain of image captioning using deep learning. So moving ahead and transitioning to the domain of remote sensing image captioning, there have been quite some works, down the line in the last 3 to 4 years. So many of them have largely dependent on deep learning. So the idea again remains the same, wherein one part of the neural network is essentially used to translate the image into a set of features, and those image features are then fed as an input to a decoder, which is a recurrent neural network based decoder. So talking about the specific work that we are viewing on the slide, the encoder is a normal convolution neural network that essentially translates the image into a set of features, and the decoder takes as input those features and tries to generate a set of words that would mean an English language sentence, right? So let's take a look at the specific examples that have been presented in this slide. So if we take a look at the first image on the left hand side, so that we can see, as humans, we are easily able to understand and deduce the fact that this is probably an airport hangar wherein there are many airplanes which have been parked. So the neural network that was proposed by this particular research paper was able to generate this English language sentence saying there are several big airplanes on the airport, right? Taking a look at the image on the right hand side. So as humans, I think it's safe to say that this is probably an image of a sea, right? Sea or an ocean perhaps, and there are possibly two water transport ships maybe, and there is a trail of water that we can see in the image, right? So we as humans were easily able to deduce these. But as the neural network, the system that was proposed in this research was able to say that there is one ship on the sea. Similarly, the other two images have been, transcribed by this neural network. So one important point to note here is the fact that although these systems that have been proposed that leverage deep learning have been successful in transcribing the remote sensing scene, or even a multimedia scene for that matter, in a single sentence caption, right? But what we are actually, or this research that we worked on, focuses on translating the entire remote sensing scene with context in multi-sentence scene descriptions. Okay, so that there is a comprehensive understanding of the remote sensing scene, both at the machine level and as well as the human level. So with that objective, we ask this question: if not deep learning, then what, right? So one important point here that I would like to stress on is, in no ways I am discounting deep learning, right? Deep learning has had a phenomenal success down the line across variety of domains. But we also need to understand that there is a new branch of research that is coming up, which is, advocating the fact that neural networks do need to be fed into some background knowledge, which we as humans inherently have, right? So that background knowledge that requires to be fed into an AI-based system is essentially what we are alluding to as knowledge graphs. So with that understanding and the need of knowledge graphs being elaborated, let's take a look at some of the popular knowledge graphs that have been out there. So I have titled the slide as knowledge graphs to the rescue. So these are some of the popular knowledge graphs that have been published on the web. DBpedia is a great resource and a huge body of knowledge graph that is available on the web. Wikidata is another. Freebase, GeoNames, Yago, ConceptNet, OpenAI are some of the other popular knowledge graphs that are out there. So let's take a look at some of the applications, that we as researchers and general public have been actually interacting with knowledge graphs so far. So I'm sure most of you would have observed that Google search, right, has been moving from depicting only search results on their web page to giving out more information about what the user is searching for, right? So in this particular screenshot that you see, so the search query that was fired was actually Taj Mahal. And so on the right hand side, you can see there is some information about Taj Mahal. There is a map and there is a geolocation where Taj Mahal is located. There are other attributes such as height, open, address, architectural style, and so on. Another important point to note here is there is also a section of see results about, and there is some musician named Taj Mahal, right? So we as users definitely are not looking for some musician named Taj Mahal, right? We are interested in the monument that Taj Mahal is. So this understanding of what the user has typed in and the contextual semantic level is important, and what it is rightly identified by technology giants such as Google and Microsoft. And that is why they are also, transitioning slowly to leverage knowledge graphs and deep learning in tandem. So let's take a look at one more example to understand this better. So if you nowadays, if you type in a name of a popular personality, right? So Marie Curie or APJ Abdul Kalam, you would be presented with a lot of information in a knowledge panel, as Google terms that section on the right hand side of the web page. So this essentially is knowledge graphs at work at a background. So you can see Wikipedia has been quoted as a source, right? At the description of Dr. APJ Abdul Kalam here. So we did talk a bit about Wikidata, right? So Wikidata is a knowledge graph that is equivalent of Wikipedia, which is largely leveraged by most of the search engines out there. So these search engines query the knowledge graph and then try to present this information in a manner that is understandable by humans, right? So the attributes such as birth, death, full name, what were the awards that that person received, education, and so on, are easily presented in a form that is understandable by us humans in these search engine results. Great. So I would definitely encourage all of you who have been listening to this session to go ahead and look at this particular blog post that Google had published. The title of this blog post is "Introducing the Knowledge Graph: Things, Not Strings." So I would want to drive and stress this point here that nowadays machines are not treating words as mere strings, but they are trying to understand that these are just not some set of characters that constitute a string, but rather they are actual things in the physical world, right? So that is where the current focus of research in the human computer interaction is also going towards, right? And knowledge graphs is definitely envisaged as a big contributing factor in that direction. Great. uh, so with that, let's move ahead. So we did talk a bit about knowledge graph, right? But earlier we were talking about scene understanding. So it's now important to bridge these two concepts of scene understanding and knowledge graphs, right? So let's quickly recap and discuss the objectives that we had earlier formalized. So I will quickly run through the major objectives that were we are looking to translate a scene in a form that is machine readable. It should be queryable by machine. We are looking to translate and represent a scene which is in a human readable form. So what we desire is a natural language scene description. And lastly, we would like to query the scene in a human readable form, that is ask questions in natural language to the machine by giving the image as an input and expect the machine to answer those questions, right? So with these objectives in mind, we proposed this whole new research area of semantics driven remote sensing scene understanding framework. So this was a framework that was built during my doctoral research with in collaboration with my colleagues at my lab at IIT Bombay. So I'll be running you all through this particular framework that we developed. So we titled this framework as SEM-RSSU for short, semantics driven remote sensing scene understanding. So let's talk a bit about that more. Great. So this is the systems architecture of that framework. So as you can see that we have also published this framework in a couple of conferences and in a journal. So let's discuss this framework layer by layer to understand how a remote sensing scene can be translated into a knowledge graph, and the knowledge graph, how can that knowledge graph then be leveraged to suit our objectives of translating the knowledge graph to a natural language scene description, to be able to ask questions over it, and also to be able to visualize it in an effective manner. Okay, so let's get started. So the framework starts at the scene ingestion layer here, wherein the remote sensing scene in a raster format, right? So is ingested into the framework. The first component in the data mediation layer is the deep learning based multi-class segmentation. So the idea is to know which segment a particular which class a particular segment belongs to. So we leverage deep learning for that. And post that comes the linked data generator, which essentially translates the classification map generated by this deep learning based component into a knowledge graph. And then comes the part wherein we use the background knowledge in the form of ontologies to enrich this knowledge graph, to introduce the notion of context in it. So essentially, it is the part where we as humans are teaching this machine to understand the context, to comprehend like what it is that the machine should understand specifically. So we'll talk about this more. But this is the semantic enrichment layer, which is essentially going to teach the machine the context of data that needs to be understood. And then comes the natural language processing layer, which translates the generated knowledge graph into a natural language sentence. And at the rendering layer comes the rendering of the output in the form of natural language scene description. There is a grounded visualization and a geosparkle query interface. So let's take a moment and try and understand the semantic enrichment layer in detail. I would like to reiterate the fact here that till the data mediation layer, the raster is actually translated into a knowledge graph. And then this knowledge graph is enriched with the ontology as a background knowledge to convey the context and the spatial aspect of the particular data, right? So let's get into the details of each and every blocks in this framework. Great. So to start with, let's discuss the linked data generator. So you can see that on the right hand side, there is a raster, right? So this essentially is the output of the classification map here. So, uh, so you can see that the red pixels are the buildings, the gray ones are the roads, the green ones are the vegetation, and the brown is essentially the flooded region, right? So this particular framework of SEM RSSU was largely focused on the specific use case of urban floods, wherein the input images were of an urban flood event. To be precise, it was the Srinagar floods of 2014, wherein we intended to, have the machine understand what is actually going on the ground, make uh, inferences based on the context and the ontologies that were fed into it, and ultimately result into actionable insights for the data disaster management and mitigation personnel. So with that objective, this particular framework of SEM RSSU was formulated. So taking a look again at this slide, the idea here is to translate this particular raster, right, the classification map, into a knowledge graph. So on the left hand side, the code snippet that you see is essentially that of a knowledge graph. So you can see that this small white colored uh, region that has been correctly classified as a vehicle is actually translated into its knowledge graph equivalent in this manner. So RDF that you see here in this XML based representation stands for Resource Description Framework. So it is one of the ways in which you and me as researchers can represent knowledge graphs in a form that can be shared, right? So so resource description framework stands for that. And so R40 is the unique object ID that has been assigned to this particular white colored region that you see here. We say that it is of type region. It has a attribute of has land use land cover as vehicle, and it is also of type vehicle. Similarly, the region R94 is of type residential building and so on. So each of these regions have been individually translated from the raster to its knowledge graph equivalent, and at the same time the geometric attributes, right? So the centroid, the bounding box, the very geometrical boundary of a particular region is also stored in the knowledge graph for further querying. So this was the first component, and of course it to a lot of extent forms the backbone of this SEM RSSU framework that we talked about in this slide. So the link data generator component was the component that we just saw in much more detail, wherein the raster classified map was essentially translated to its link data representation, that is the knowledge graph of a remote sensing scene. Great. I'm hoping that the data mediation layer has been understood so far. So with that, let's move and elaborate on the semantic enrichment layer, wherein we'll be taking an example to understand how a particular knowledge graph is enriched both on a spatial and contextual basis. Great. So this is the magnified view of the semantic enrichment layer, wherein the context aspect is particularly added to the knowledge graph. So on the right hand side that you see here is the particular example that we will be elaborating on. Great. So let's get started. So as we discussed in the earlier slide, the data mediation layer, right? So you can see that the RDF data representation of remote sensing scene knowledge was the output of the data mediation layer, which served as an input to this semantic enrichment layer. So to give you an example, so what was actually inferred from this particular data mediation layer was that there are individual regions called vehicles belonging to the type vehicle, and there is an individual region of the type road, right? So this was the information in the knowledge graph after the data mediation layer. Now comes the semantic enrichment layer, where the machine should try to understand and form relations between these individual regions that were detected in the data mediation layer. So how does it do that? Let's talk a bit about that. So in the first layer of this particular semantic enrichment layer is the spatial knowledge enrichment, wherein the domain knowledge resides in this particular ontology called the remote sensing scene ontology. So this ontology was proposed as a part of our work, wherein we formalized the spatial relations that can exist between two particular regions in a remote sensing scene. So this was formalized through axioms and rules that have been embedded in this ontology. And then comes the deductive reasoner component, which takes as input the unenriched knowledge graph, the example that you can see here. In combination with the remote sensing scene ontology, it tries to enrich the knowledge graph by inferring directional and topological relations between these regions. So you can see that what were individual regions called vehicles and roads are now connected with one another using this particular relation called geo-NTPP. So it essentially, the full form of NTPP is non-tangential proper part. It is one of the RCC 8 relationships, which is the standard to represent, the spatial relationship between two entities, right? So the machine was actually able to infer that the vehicles are connected to this road region through this geo-NTPP relation. Great. But as humans, we are not uh, we do not know, or rather this particular term of geo NTPP is a jargon to most of us, right? So we would want this particular name of the relation to be translated in a manner which is very intuitively understood by all humans. So that this is where comes in the contextual knowledge enrichment layer, wherein the flood scene ontology was proposed by our research group. So the idea of the flood scene ontology was to formalize the different concepts that proliferate during the flood scenario, right? So this served as the background knowledge in combination with the semi-enriched knowledge graph, which was spatially enriched, given as an input to the deductive reasoner, was able to add the context and the spatial aspect to it, right? So two important terms were essentially inferred in this layer. So the geo NTPP relation was translated to the on relation. So we can say that vehicle 1, vehicle V2, Vn are on, and the road was essentially translated, or rather specialized, to an unaffected road. So the important point here is that the the understanding of the road being unaffected in context to the flood scenario was understood and inferred by the machine, right? So with that understanding, we move ahead to the scene knowledge aggregation layer, wherein the idea was to aggregate the knowledge in a form which is more intuitively understood by humans, right? So that is where we propose the spatio-contextual triple aggregation algorithm. So the sole purpose of this triple aggregation algorithm was to uh, club different entities in the knowledge graph to a more intuitive collective entity, which is understood by humans. So to give you an example of the aggregation, multiple vehicles at a certain distance from one another on an unaffected road essentially would mean that there is traffic congestion, right? So multiple vehicles aggregated to form one single collective entity of traffic congestion. And what started out as individual regions called vehicles and road essentially ended up, after the enrichment process, being traffic congestion on an unaffected road. So I hope that the enrichment aspect of how individual regions that a deep learning model understood were translated and enriched with both spatial and contextual aspect to convey that there is traffic congestion on an unaffected road, right? So with this enrichment, I hope that it is understood that it is relatively simpler to translate this particular triple of traffic congestion on an unaffected road to an English language sentence, right? So a sentence such as there is traffic congestion on the unaffected road can be easily derived by using a simple templating mechanism if this particular state of knowledge enrichment has been achieved. So that was what was proposed in the further layers of natural language processing, right? So we talked about the data mediation layer, where we elaborated on the process of translating a classification map to a knowledge graph, and how the knowledge graph was hierarchically enriched, first with spatial semantics, then with contextual semantics, and the last layer being aggregation, which served as an input to the natural language processing layer, which essentially generated the natural language scene descriptions. Right. Another advantage of using this knowledge graph approach for generating these natural language scene descriptions is the explainability aspect. Right. So I'm sure most of you might be aware that this particular research area of explainability is becoming popular because of the fact that deep learning largely acts as a black box, right? So if knowledge graphs are used in tandem with deep learning, there is a way to explain and understand how the machine was able to derive new concepts based on the traceability of how knowledge graph was enriched, right? So with that understanding, we developed this front end for the framework that was implemented by our research group. So you can see that the on the left hand side there is a file browser panel, and multiple files are listed here. So these files are essentially satellite images, right? There is a preview panel on the bottom left that you can see, and then there is a button called render grounded scene descriptions. So if on the clicking of this button, what happens is the framework runs at the backend. It generates the visualization of the remote sensing scene along with the scene description in the English language. So I would like to bring your attention to the fact that this is not just merely translating a raster image into its natural language the scene description, but rather the explainability aspect of it is also included in it. So if we pay attention here, you can see that this sentence, there is a road, right? It is highlighted in the color gray, and it is essentially mapped to this gray region that you see in the scene, which is also highlighted in gray, right? So this is the road that this particular sentence is talking about. So if we move ahead, there are accessible buildings along the road. So this sentence has been highlighted in blue, and correspondingly, you can see these blue regions. So these are the accessible buildings along the road that this particular sentence is talking about. Similarly, there are flooded buildings to the west and the east direction. So I would like to bring your attention to the fact that the machine was able to understand the spatial relation of west and east in context to the road, right? There is traffic on the road. There are stranded vehicles to the west direction of the road. So I'm not sure if it's visible in the slide, but the region that I'm pointing to with the cursor is actually colored in green. So these are essentially the standard vehicles that are to the west direction of the road, and there is flooded vegetation to the west and east direction of the road. So this was the final output of the framework that we developed in a research group. And at the right hand side, this is a geosparkle query. So to give you a brief introduction, geosparkle is essentially the query language that is used to query over knowledge graphs, right? So what SQL is to databases, geosparkle is to knowledge graphs or graph databases. So this was just for the sake of transparency that we added this geosparkle query panel, wherein we could type in a query and get the result and visualization of the geosparkle query. Great. So this was one of the prominent works in the domain of semantics-driven remote sensing scene understanding, which fulfilled the two objectives that we had of translating a remote sensing scene into a natural language scene description, and also to translate a remote sensing scene into a form that is both human readable as well as machine understandable, right? So the knowledge graph aspect. With that, let's talk about the third objective that we had, wherein we expected the machine to be able to answer questions posed to it in natural language, right? So this was another research study that we worked on. So this also has been published in an prominent IEEE conference. So the idea was to ask the machine questions in the English language and then expect the machine to run the query and provide the output in the form of visualizations, right? So to give you an example, so the natural language question, which are the areas that have mixed forests adjacent to mineral extraction sites? So this question, if posed to the machine, the idea was to run this question over the knowledge graph. And as we know that knowledge graphs only support geosparkle, or perhaps if you to be more specific, if you are looking at the implementation side of things, Neo4j is another popular graph database that is up and coming. So Cypher is the query language that Neo4j generally uses. But the fact remains that there is a need of a mechanism to translate an English language question to its query equivalent, right? So this essential problem was tackled in this research study, wherein we strive to translate this English language question to its geosparkle query equivalent. So the approach that we used for this particular research study was neural machine translation with attention. So the idea was to take this entire set of words in the English language and have the machine generate its geosparkle query equivalent, right? So we had a decent success at this research study. So that was one of the prominent research works in regards to natural language question answering over remote sensing scenes. Another important research that we pursued in our lab was to try and visualize the remote sensing scene knowledge graph that we were generating, right? So this was another work that was published in an IEEE conference. So the idea was to be able to try and parse the knowledge graph that was generated by our framework and have the user intuitively interact with it. So for those who are interested, this tool that we developed has been hosted on our lab website. So the URL is geosysiot.in/tools/rskg-explorer. So you can even take a look at the data source, that we are using. So if you click on this hyperlink, you will be presented with the knowledge graph. And so the most important bit in this visual exploration tool that we developed is the aspect of intuitive interaction with the user. So each of these nodes in the knowledge graph are clickable. And if you click on this node, you are presented with the attribute and metadata information related to that node. So this was the research advances that I wanted to share with you all through this platform, which essentially fulfilled the three research objectives that we talked about earlier. The objectives of translating a remote sensing scene to a knowledge graph equivalent, to have it translated to a natural language scene description, and the last bit wherein to develop intuitive interfaces of exploring knowledge graphs through natural language question answering and through visual exploration. So with that brings us to I think the last slide of the session, wherein we would discuss the other applications which we foresee can be applied for when the remote sensing is driven by knowledge graphs. So disaster monitoring is of course a great application wherein the context plays a significant role, right? And then there is agriculture. So agriculture too, we foresee numerous applications coming out of knowledge graph driven remote sensing, wherein intelligent crop recommendations, disease prevention, mitigation, and most importantly, integration with numerous data sources can be achieved if the domain of remote sensing is driven by knowledge graphs. Some of the other applications that we foresee are urban sprawl monitoring and hostile territory monitoring, wherein specific details about the background knowledge would need to be encoded in an ontological manner so that the machine can infer new knowledge and enrich the knowledge graph further for the specific application. So I think that is the content that was planned by me for this session. So with that, I would like to end the session. Thank you all for listening. So I guess we have some time so we can take questions too. Thank you. Thank you, guys.
Yeah. Thank you, Dr. Abhishek. Thank you, sir. Really, very participants have really enjoyed and learned a lot from your session. Now the question session is on. If anybody has any question, you can ask. If you want, you can write in the chat. I'll ask to the sir. Sir, I want to ask one query, sir.
Sure.
I want a suggestion from you, sir. Like you have used the clustering, right, in the satellite image, and then you assigned this is the vehicle, this is the road, So, so for clustering, you applied machine learning, and for finding out what are the objects, you assign another machine learning, right, sir? Am I right?
Yeah, so the idea was to use deep learning for the problem of classification, right? So translating a particular segment in the image to a particular class. So that was where specifically we leverage deep learning. So I think the other
Right.
word for this is semantic segmentation, right? So the idea of assigning
Hmm.
labels to each and every pixel in the image. So that was what like was achieved through the deep learning, and then of course the knowledge graph component with the reasoning took over. Yes.
Right,
So
sir.
yeah.
So assigning the like label,
Mm-hmm.
actually, like you are working on the particular application, right, sir?
Mm-hmm.
Flooding.
Correct. Yes. Yes.
uh, but like in any in nature, like we human understand any scene, sir. So what is the current state, right? Because the deep learning only like train for the flooded area, vehicle, road, and then if we
Mm-hmm.
want to use for the another application, we need to train for another thing. So
Absolutely.
from,
Mm-hmm.
yeah, from your experience where we are now, sir, like your expertise in this field in scene understanding, so like we are far behind the understanding of scene like a human.
Okay. Yeah, that's a great question, Dr. Joshi. So the idea is that, of course, as you rightly mentioned, that for different applications, different neural networks would need to be trained, and that is why the
Yes.
whole research area of domain adaptation and transfer learning is blossoming, because we want to generate a neural network that is generic enough to be able to translate images to its corresponding labels, right? But having said
Yes.
that, my personal experience is that uh, like specifically, because this particular research study was for the domain of floods, right? So we trained our deep learning model specifically having the machine look at remote sensing scenes of urban flood. So it would work on a normal setup to wherein there is no flood, because most of the classes would overlap on that aspect. But if we were to talk about a specific application, like, so for example, forest fires is a great application, right? So
Yes.
definitely our deep learning model would not scale
Yes.
on the application of forest fires. So yeah, so talking about that, I feel that of course there is a need for being application specific when we are currently restricted to a particular research study. But of course, there is research going on in the direction of developing general
Generate.
neural network. I think the research area is AGI, right? So artificial general intelligence. So that is where researchers are actually seeking so far. Yeah.
Yeah. Thank you very much, sir, for
Thank you.
suggestions.
Thank you. Yeah.